So yesterday you watched the recording of the lesson on universal wave equation. Were there any problems with that? Any questions we have regarding how the universal wave equation works? Okay, I'll let you dig it out. See if from that worksheet if there were any problems that gave you trouble there.
I wasn't here yesterday.
Okay. Anybody else need the worksheet from yesterday? Okay, so if any questions from the worksheet? Okay, what about echo questions? Did we get those? Okay, the only trick with an echo question obviously is that the waves travel there and back again, so you've either got to divide the time by 2 or the distance by 2, okay, if it's talking about there and back again. Right? The other place where sometimes people struggle a little bit is in those questions where it talks about, you know, like there's these 2 boats, okay, and they're on the ocean. Like one boat is in a trough and the other boat is on a crest, and there's a crest between them. Okay, and then they tell you they're like 20 meters apart. What are they giving you the ability to calculate with that? Did you guys do any like this? Yeah, I'm pretty sure there were some in there. But okay. This is going to give you the ability to calculate wavelength, but it involves understanding properties of waves. How many wavelengths apart are these 2 boats? Okay. This is how universal wave equation questions are going to go. I know you guys can manipulate v equals f times lambda. Okay, like that's not a hard thing. What's going to try to trick you is context. Okay, the one wavelength is the distance between any 2 equal successive points on a wave. So that's one wavelength. How many more wavelengths are there here to the other boat? Half. So 20 meters equals 1.5 wavelengths. Can I calculate the actual wavelength now? Right, 20 divided by 1.5. Now I know how many wavelengths apart they are. Okay, the question would also tell me something like the people in the boats bob up and down once every 8 seconds. Okay, what did they tell me there if they bob up and down once every 8 seconds? Period. Okay, because they told me how long it takes for them to go over a crest and under a trough and back to the next crest, up and down. That would be one complete cycle. Okay, 8.0 seconds. Question would ask me, what's the speed of the waves? Right, so then I would go, okay, universal wave equation can come in 2 forms. This form, that's what's on your formula sheet, but that also means this, because F is 1 over T. Since I have lambda and T now, well, actually I don't have lambda because I never did the math. Okay, so 20 divided by 1.5. All right, so there's our wavelength. Okay, I'm looking for speed, so I just divide that by the time. So divided by 8. Those waves are moving at 1.7 meters per second. Okay, everybody all right with a question like that? Okay, those are the kind of universal wave equation questions you could expect on a quiz or an exam. Okay, they're not going to be simple ones like, here's a wave with this frequency and it's going this fast, calculate the wavelength. They're never going to be that simple. There's always going to be a context, an echo, 2 boats in the ocean. Okay, those kinds of things are always going to be the context of a wave equation question. Now, wave equation is universal. That means it's going to apply to everything we take for the remainder of the unit. It's going to apply to Doppler effect. It's going to apply to air columns, to interference, all of that kind of stuff. It's all going to be part of that. Okay? So there's going to be many, many applications of V equals F times lambda or lambda over T. Okay? Because we use it a lot. Okay, how far did we get on that worksheet yesterday? Anybody get more than half done? Okay. What I would like you guys to do then, I'm just going to pull it up here, and I'm going to pick a few questions that I want you to do before we move on to interference. Just because that concept is so very important. Okay, I would like you guys to do, let's say, 10, 13, 18, 21. Okay, now something else that probably came up yesterday here, guys, just to mention it. If you are dealing with sound or light, okay, light waves are always going to travel at what speed? Light might be in the answer. Light speed, okay? Light speed is on your formula sheet. It is 3.00 times 10 to the 8 meters per second. That is for light, radio, microwaves, X-rays, okay? Or any electromagnetic wave. Okay, all electromagnetic radiation is light and thus travels at the speed of light. Okay, so if you see those terms and you're not given a speed, it's because you are given the speed. Those are forms of EMR, electromagnetic radiation. Okay, the other thing is sound waves. Sometimes you'll be told the speed that sound is traveling at, and other times you'll be told the air temperature the sound is traveling through. As with all waves, the nature of the medium is what determines their speed. For sound, temperature of the air it's traveling in affects how fast it travels. The warmer the air, the faster the waves can travel. So you have a formula on your formula sheet that looks like this. V equals 332 plus 0.6 times big T. Here's the confusion. That big T does not stand for period. It stands for temperature in degrees Celsius, not Kelvin. Okay? That's why this works even for temperatures below 0. You'll get a negative number and be adding a negative and the speed will slow down. This is the speed of sound at 0 degrees Celsius under 1 atmosphere of pressure. Okay? They're never going to give you atmospheric pressure because that's another formula, so you can assume all things are done at 1 atmosphere. Okay? So 332 plus 0.6 T, okay, is going to give you the speed of sound in any air temperature. Okay? All right. So I'll put those questions back up. 10, 13, 18, and 21. You've got them from the sheet, so I don't need to make this either. Okay. All right, so now we're looking, today's lesson is going to be more about wave behavior. Okay, there are some calculations involved here, okay, some universal wave equation stuff, things like that, but mostly, okay, we're looking at the behavior of waves during a time when they try to overlap each other. Okay, remember that waves are energy. Unlike matter, they can occupy the same position at the same time. Matter can't do that, but waves can. However, waves have to travel through something. That means that the medium, if it has more than one wave trying to travel through it at once, needs to represent the energy in some way. That some way is the amplitude and or the shape of the medium as the waves try to move past each other. This is kind of why the ocean looks the way it does. If you've ever been out in the deep ocean, the waves are kind of everywhere, right? The ocean's just kind of doing this random thing, the waves are kind of everywhere. That's because the waves are kind of everywhere. Okay? They're overlapping each other, traveling through each other, passing around, and that happens. And the ocean, the water, tries to take the shape that represents the amount of energy that's in that particular location. Okay? So there are effectively two types of interference. Constructive interference, where the energies align and the amplitude gets bigger. And destructive interference, where the energies don't align, okay, or they're out of phase is the terminology we use, and the amplitude is decreased. Okay? We use this in modern technology all the time. Anybody got a pair of noise-canceling headphones? Okay. If you have true noise-canceling headphones, that's the ones with the microphone on the outside. Okay? Those use the principle of linear superposition, that's what we're going to talk about today, to cancel the noises in the ambient space around you. Okay? They detect the frequency and the wavelength of the waves of the sounds that are in your surroundings, and they produce the exact opposite sound actively to cancel them out. Because if they produce a wave that's up and they're receiving a wave that's down, they cancel, eliminating actively the noise from outside. So active noise canceling works with a microphone, detecting sounds from outside, and your headphones producing an opposite sound to destroy, temporarily, okay, or at least at your ear, the sounds that are outside. Okay? That's how active noise canceling works. Passive noise canceling is just insulation. Okay? It's just trying to deaden it. A car's muffler, okay? Also designed to use destructive interference to cancel the sound of the engine, as the guy in my neighborhood with the straight pipes doesn't understand. Okay? Goes around, flooring it and rattling the windows in the neighborhood. Okay? So mufflers are designed to cancel noise. Okay? They reflect the waves around in such a way that they end up interfering destructively with each other and canceling each other out. Musical instruments of the acoustic nature use constructive interference. They use something called resonance. Okay? And they make the waves bounce around inside the resonance chamber. So on a string instrument, that's the hourglass-shaped body. Okay? The waves bounce around in there and they interfere constructively. Okay? The whole cavity resonates at a higher amplitude than the string that was plucked, producing a louder sound. Okay? Kind of like if you've ever played an electric guitar, but you don't turn it on. Okay? So there's nothing to power. You just pluck the string. It hardly makes any noise at all. Okay, because there's no pickup, no microphone there to take it to the amplifier and make it louder. Okay, on an acoustic instrument, that little thing, the waves go inside and they interfere constructively, they come out louder. Okay, everybody okay with that? All right, so we're going to talk about the two kinds of interference, what they look like, and look at a few situations where they might apply. Okay? All right, so interference and linear superposition. Linear superposition is the scientific way of talking about what happens when two waves are in the same place at the same time. Okay, what happens when they overlap. Okay. So, straightforward way to deal with situations where two or more waves go through the same place, okay, gonna look something like this. Okay, so on the left here, we have two pulses traveling towards each other, and they are both up. So they would both have an amplitude of, let's say, +1. When they travel towards each other, they're carrying energy along the spring. When they overlap, that energy has to be conserved by the spring. So instead of having two separate waves with an amplitude of +1 each, for an instant, the slinky has an amplitude of +2. It has to show. That's the amount of energy that's traveling through the string, or the spring, sorry, at any one point. Okay? But when they occupy the same place, the amplitude gets bigger. Now here's the thing about waves. Because they can occupy the same place at the same time, because they're energy, they also pass right through each other. Okay? They don't destroy each other. There's only interference at that location. Okay, so they only interfere there. You may have had this experience if you had Bluetooth headphones on and you fired up your microwave. Okay, the microwave and your Bluetooth headphones often operate on very similar frequencies. They'll like cut out a little bit if you're close to the microwave. If you move a little ways away from the microwave, okay, you won't feel that anymore because the interference was close to the source of the interfering waves. Okay, making some sense there? All right, so it would temporarily have this shape, but then the waves would travel on exactly as they were before. They don't reflect off of each other, okay? Wave A is traveling to the right. Even after it interferes, wave A is still traveling to the right. Wave B is still traveling to the left. They pass right through each other, okay, on their way by. Everybody all right with that idea? Okay, the opposite is what we call destructive interference, and that's what we see on the right-hand side. So I've got wave A that has an amplitude of +1, wave B with an amplitude of -1. They travel towards each other, and in the instant where they overlap, their energies cancel. Okay? The resulting shape of the medium reflects the energy that was on the medium at any time, and that's 0. Okay? And after they interfere, they travel happily on as they were before. Wave A to the right, wave B to the left. Okay? So interference is not a permanent destruction of waves. It is a overlapping of wave energy at a given point. Right? Now, most of the time the interference that we deal with is pretty random stuff. Okay? And it's usually, not good. Okay? If you've got the microwave interfering with your headphones, things like that. Okay? I mean, back in the day when Wi-Fi was more like Bluetooth, if you fired up the microwave while you were trying to use your Wi-Fi went out. Okay? Now Wi-Fi is on a different wavelength and frequency than microwaves are. It's a real problem. Okay? That sort of making sense? Okay? Anybody ever have a point where they lose their cell phone reception even though they seem like they have good reception, like on their bars, but your phone gets interfered with? Okay, same deal. There's just something in the area that's overlapping on a similar wavelength and frequency with yours. Okay, why is the cell reception here so bad? Actually, it's not. It's bad here on Saturday. Here's why. The location of the nearest cell towers. Okay, so here's the school. It looks like a house because that's all I can draw. Okay, nearest cell tower is down here. It's not a person, it's a tower like that. It's transmitting energy. There's no line of sight to that tower, or a really bad one. Okay, you ever notice how the parking lot is absolutely the worst spot along with the hallway right by the cafeteria? Okay, but if you go out onto the road and head that way, it gets better. Almost before you're even to the condos over here, because suddenly you're a line of sight again to the tower. Okay? It's not an interference thing. Lots of people say, oh, it's got to be interference. It's got to be there's so many people in the school. But like I say, it's bad on a Saturday. It's not an interference thing. It's a line of sight thing. Okay? They had proposed years ago to put a cell tower up here, but people didn't like that. There was this group of people who said cell towers cause brain tumors. And they were a very loud, uninformed group. And they got it kiboshed, which is why there's no cell tower up here, and there really needs to be one. And they don't cause brain tumors. Okay? Mrs. Ostafchuk, who was the principal at the time, actually came to Mr. Dickey and myself. She's like, you're the physics guys. Is this for real? And we're like, no, it's not. Because wave intensity decreases exponentially with distance, just like gravity. And yeah, we showed her that even if you were sitting on the tower, you weren't really, if you were more than like 3 meters away from the actual transmitter, you were fine. Okay? If you were sitting on the transmitter, your butt might get warm. Okay? But it probably wouldn't kill you if you didn't stay there. Silly people. Okay? Oftentimes, though, the uninformed people are the loudest. Okay? So it's not an interference thing. Okay? It's just a line of sight thing. But obviously, there can be interference. It depends where you go. It depends what kinds of things are interacting. This is how jamming works. Okay? If you've ever heard, like, you watch like Top Gun or something like that, they'll try and jam radar, or they'll try and do these things to interfere with the radar. Okay? To jam radar, all they do is just flood the airspace with all frequencies and wavelengths of radio waves. And that will interfere with the ability of that radar to detect them, okay, things like that. All right, does that sort of make sense? Okay, so jamming just involves throwing out a whole bunch of frequencies to interfere with the use of other radio frequencies. Okay, there were some restaurants early on when cell phones came out that actually had small active jammers because they didn't want people on their phones in the restaurant. They felt it was not part of the experience, and now there's influencers who take pictures of their food every time they eat. Okay, but you can do that. You can actually get little cell phone jammers, okay, that will keep cell phones from working in certain areas. Okay, and all they do is just generate waves that are similar but opposite to most cell phone frequencies. All right, so I'm going to show you here now a video we took a few years ago. We just used the slinkies, but we could slow it down so you can actually see the interference happening. Otherwise, I'd just do it on the floor again. But this one you can see a little better just because it's slower. And it's mine, so I can play it.
1, 2, 3.
Okay, so what kind of interference was that? Constructive or destructive? Destructive, right. So we both produced waves, okay, but they were opposite in their amplitude, okay? And you can see, okay, when they go towards each other, right, there's that moment where when they overlap, and it's not perfect because we didn't make them exactly the same amplitude, but it's pretty close, okay? The spring goes straight, but then afterwards, those waves travel on exactly as they were before. Okay? His wave was a little bit longer, but a little shorter, like shorter in amplitude, not as high or tall as mine. Okay? Mine was a shorter wavelength, but had a greater amplitude. That's how you can tell them apart after the fact. Okay? Those are still the original waves that were produced. They pass right through each other after that point of interference. Okay? So that's what destructive interference would look like, okay? Kind of in motion. There's that point right there where they destructively interfere, and then they move on just fine. Okay, so now we're going to do a constructive one, I think. Yeah. So both the waves are out to the left. Okay. You can see the spring clearly takes on the full energy, okay, of the two pulses. Okay, so there it's taking the full energy of the two pulses, and then the two pulses pass on perfectly fine after the fact. Okay? Are you okay with that? Okay, I'll get you to turn that light back on. Thank you for that. Okay, so the principle of linear superposition goes like this. When two waves occupy the same space at the same time, you add their amplitudes to get the resulting shape of the medium. Okay? It has to conserve the energy, the wave energy that's present, so it has to assume the amplitude that would be the sum of the two wave energies. Okay, so we have +1 and -1, the sum will be 0, like you see in the diagram on the right. Okay, if you got two going towards each other that are +1 and +1, then it has to take a shape of +2. Right? Pretty straightforward. I almost always, and by almost I mean every single time, ask a question like this on the unit exam. Like, draw the resulting shape of the medium when these two pulses interfere. Okay, pretty simple thing to do. Okay, you just add the amplitudes and draw what it will look like. All right, so that's the principle of linear superposition. Okay, the slinky or medium, whatever it happens to be, will take the shape that is the sum of the shapes or amplitudes of the individual pulses. Okay, so when they overlap exactly, okay, so if these two are headed towards each other, when they're both right here, okay, then obviously the amplitude, okay, would be one tall wave, okay, and here when they overlap, the whole thing would be flat. Okay? Everybody good with that? Okay, now the same is true, like we've kind of simplified this. You never get just one pulse and one other pulse coming towards each other. You usually get a train of waves, or a wave train, okay, interfering along the same medium or traveling along the same medium. Okay, so on the left again is constructive interference. Okay, these waves are what we call in phase. Okay, constructive interference occurs when waves are in phase. That is, when one is up, the other is up. When one is down, the other is down. They match. Okay, that's what in phase means. All right, so the resulting pattern of interference for waves that are in phase is constructive. Okay, so this one has like an amplitude of +2, this one has an amplitude of +1, so this has an amplitude of +3. Okay, this would be -3, +3, -3. Okay, because this would obviously be -1 and -2. Right? So that's the kind of thing I could ask on a test. Put these two waves and say, what's the resulting wave? You draw it. Be this one. Okay? For destructive interference, okay, so now I've got this one that's +2, -2, +2, -2. This one's -1, +1, -1, +1. Okay? Are those in phase or out of phase? They're out of phase. When one is up, the other is down. Okay, so out of phase results in destructive interference. Okay, and that's why the resulting waveform would only have amplitudes of +1 and -1. Where one is +2, the other is -1. So the resulting waveform would be +1. Okay, questions on that? Okay, so this in phase is a term we're going to use a fair amount here. This is an application that we see quite often if you're looking at like professionally installed home theater systems, you know, fancy movie theaters with the, you know, the incredible sound systems and things like that. They're going to not only position their speakers in certain places, but they're also going to program them, okay, so that as sounds are emitted, there can be delays of that sound being emitted from certain sides in order to ensure that every seat in the theater is receiving the best quality sound. Okay, so that we're getting constructive interference at basically any point in the theater. Because if we don't place the speakers properly and delay the emission of certain wavelengths, we won't get that. There'll be some seats that suck, okay, in terms of their sound quality. And obviously nobody wants to pay the exorbitant sum of money you pay for a movie ticket these days, okay, and have crappy sound. So they're designed in a way that makes it basically a really good experience for anybody in the theater. Now, does that mean there are still going to be better seats than others? Where's the best seat, sound-wise, in the theater? Dead center. Top to bottom, side to side. Those are the best seats, okay? Because they are going to be at the point where everything is naturally calibrated to. If you are much closer to one side than the other, that calibration is going to be a little off for you. Okay? Sound is going to be dominant from one side because you're closer to that source. Okay? The best thing is to be equidistant from the sources as much as possible. Okay? All right. So if I've got this receiver and it's just playing a constant tone, okay, so just one sound, just kind of like a dial tone kind of sound, okay, just kind of a hum. If I position a person equidistant from both speakers, okay, then they will probably hear a loud sound as a result of constructive interference, especially if I position them an equal number of wavelengths from each speaker. So this person right now, okay, is 3 meters from each speaker, and they're listening to sound that has a wavelength of 1 meter. Okay, which means there are 3 wavelengths from this speaker to the person, and 3 full wavelengths from the other speaker to the person. Which means the waves travel the same number of wavelengths and arrive in phase, crest to crest, trough to trough. They're always going to interfere constructively because they're in phase. Everybody all right with that? So that person at that position would hear a loud sound due to constructive interference. Okay? So that person is effectively located right here. Okay? What would the person hear if I put them here? Okay, so the difference in the colors there, the dark blue lines are coming from speaker B, the light blue lines are coming from speaker A. Right now, that person is on a crest from speaker B, but they're on a trough from speaker A. Okay, the troughs aren't drawn, but if they were, okay, they would look like this. Okay, so those are the troughs from speaker A. So the light blue are the crests, these are the troughs. So that person is hearing what? Nothing. At that point, they would hear no sound at all, because both speakers are emitting exactly the same waves, but they're positioned at a spot where the wave from one of the speakers is a trough, and the wave from the other speaker is a crest. And they cancel each other out at that position. Okay? Now, in most rooms, you'd never get it so it's perfectly canceled because you're going to get reflection off the walls and things like that. But if you were in an anechoic chamber, which incidentally looks like the inside of a meat grinder, it's kind of terrifying. Okay? But it doesn't have any reflections to do that. You would actually be able to walk around that chamber and find points where it's loud and where it's dead quiet, even though the speakers are still producing sound. Okay? I actually have a video of a guy who kind of did this experiment. All right, so all that guy did was move around inside of this interference pattern and find locations of constructive and destructive interference. Okay? So if we alter that first situation and I back up this one speaker, okay? So now this speaker is 3 meters from the observer, but this speaker is now 3.5 meters from the speaker, and again, we're still listening to sound with a wavelength of 1 meter. Now, sound waves from this speaker travel 3.5 wavelengths. Remember that a crest and a trough are always half a wavelength apart. Okay? So now, when the waves arrive from this speaker here, they're a trough. From this speaker, they're a crest, and now they're canceling each other out, and that person is standing at a point of complete destructive interference where they would hear nothing. Okay? Everybody with me there? What if I backed this one up to 3.5 meters? Would they hear loud or quiet then? So right now they're traveling 3.5 wavelengths from this speaker and 3 wavelengths from this speaker. If I back this up another 0.5 meter, which is half a wavelength, then it'll be 3.5 wavelengths and 3.5 wavelengths. Will they be arriving in phase again? They will. Trough to trough, crest to crest. Okay? The key that determines whether you have constructive interference or destructive interference is how many wavelengths travel to the observer from each speaker. Okay? If I subtract these two numbers and I get a whole number, or 0, okay, then they're meeting in phase. Right? But if I backed this speaker up, let's say we go back to this first situation here. Okay, if I back this speaker up to 5 meters and left this one at 3, would I hear loud or quiet? What's 5 minus 3? 2. So the difference of travel is 2 full wavelengths. So they're still going to be arriving crest to crest and trough to trough. If I back this up to 6.5, then what would I hear? What's 6.5 minus 3? 2.5. So now they're out by a half a wavelength. The waves from this speaker are traveling 2.5 wavelengths farther. That means they're arriving as a trough. The ones from this one are arriving as a crest. They are completely out of phase. So what determines whether you hear constructive interference or destructive interference is the number of wavelengths, or the difference in the number of wavelengths traveled from each source. Okay? If it's out by a half a wavelength, then they're meeting crest to trough, because crests and troughs are half a wavelength apart. But if it's a whole number, then they're always meeting crest to crest, trough to trough. Okay? It's all about the point in the wave and the difference in the number of waves traveled. Okay? Okay, so that's kind of what this diagram is about, similar to that one we looked at before. Okay? A person sitting here is going to experience what kind of interference? Dotted lines are troughs, solid lines are crests. John, what kind of interference? Constructive, yeah, it's crest to crest, right? It's crest to crest, even though from this speaker the waves are 1, 2, 3 wavelengths from the speaker. Here they're only 1, 2. But 3 minus 2 is still a whole number. Anytime you subtract the number of wavelengths from each speaker, if it's a whole number, they're in phase. If it's anything 0.5, then they're completely out of phase. I'm never going to give you a question where it's not a whole number or 0.5, okay? Because then it's like sum of each, and you can't really give me a definitive answer then. So it's never going to be like 0.33 wavelengths, okay? It'll either be a full number of wavelengths or a half, okay? 2.5, 10.5, whatever. All right, what will this person do? Virginia, what's that person going to hear? Destructive, okay? Because from this speaker here, they've gone 1, 2, 3 wavelengths, but from this speaker, 1, 2, and a half. 3 minus 2.5 is 0.5. They're out of phase because they're half a wavelength out. All right. Everybody good with that idea? Okay. Copy this example down. This is what we call a 2-speaker interference question. There's always one of these on the unit exam because it deals with interference, speed of sound, universal wave equation, and Pythagorean theorem. Okay, give you a few minutes to get that copied down, and then we'll walk through how to solve it. So we've got this diagram that says the person's directly in front of one speaker, 2.4 meters. The speakers are 3.2 meters apart. If we're going to figure out how many wavelengths there are from each speaker to the observer, what am I missing from that triangle? Adam, what do I need on there? Yeah, I need this, right? Well, I need the waves, and I need to know this distance so I can figure out how many of the waves are there. So I just got to do a quick Pythagorean theorem calculation, okay, to get this side here. So I'm going to do a C equals the square root of 2.4 squared plus 3.2 squared and get that side. All right, great. That side's exactly 4 meters long. Okay, so now I've got that. Here's the other things I know. Okay, both speakers are playing identical 214 hertz tones. What did they give me? Frequency, right? Hertz measures frequency. Okay, so frequency equals 214 hertz. And the speed of sound is 343 meters per second. Since they're sound waves, that's the speed of the waves. Okay, does the speaker hear a loud sound or no sound? Well, what determines that is how many waves from each speaker to the observer. The only way to know that is to know what about the waves. What can I calculate about the waves with the two pieces of information I have right now? Wavelength. All right, so I'm going to go V equals F times lambda and solve for lambda. Okay, so lambda is going to be V, 343 meters per second, divided by hertz. Okay, so divided by 214, so that's going to cancel the seconds, okay, because a hertz is a per second. Okay, and that's going to leave me with meters. All right, so 343 divided by 214. All right, so each wave is 1.602. We'll keep all those numbers in the calculator. Okay, I'm just going to write for right now 1.60 meters. Okay, so now I know the wavelength. But once again, what determines whether this person hears a loud sound or a quiet sound is the number of wavelengths traveled from each speaker to them. Okay? If they both arrive crest to crest, you'll hear a loud sound. If they arrive crest to trough, you'll hear nothing. So what we've got to do is figure out how many waves are there from each speaker to the observer. And we can do that because we know how long one wave is, and we know how far they have to travel. Agreed? So we'd be able to figure out how many waves there are between that speaker on the left and the observer. Okay, so all I would do is say, all right, I have 2.4 meters. How many 1.60 meter long waves would fit in 2.4 meters? So 2.4 divided by 1.6. All right, exactly 1.5 waves will fit there. All right, so I'm going to do my best to draw these waves. Okay, so they're arriving as a crest. Okay, arriving as a crest there. So 1.5 wavelengths is how many there are there. Okay, I have to do the same thing here. How many waves would be in a 4 meter distance? So 4 divided by 1.6. 2.5 wavelengths for that side. Okay, so there's one wave, there's 2 waves, and there's the half. Are they coming in at the same point in the wave? Okay, I wouldn't suggest you end up drawing this. Okay, I would just do this. There are 2.5 wavelengths here. There are 1.5 wavelengths here. 2.5 minus 1.5 is 1. It's a whole number. If it's a whole number, they're in phase. This person hears a loud sound. Okay? The last operation I'd be looking for you to do would be that. Okay? On a quiz or an exam, that's a 5-mark question. You're not getting 5 marks for a coin flip. Okay? The question asks, is it loud or quiet? It's also going to say, show your work or show your proof. If you don't show proof, it's because you didn't know how to do it and you knew you had a 50-50 chance of guessing loud or quiet. So well, if you write it's loud or quiet and you're right, you get 1. Okay? Because you didn't prove it. And I will write beside your answer, proof. Okay? So make sure you show all of these steps. So you'd get a mark for your givens, you'd get a mark for doing a wave equation calculation, you'd get a mark for doing your geometry here, your Pythagorean theorem, your number of waves calculations, and then this one here that determines whether they hear a loud or a quiet sound. Okay. All right. Is there any part of that that's mathematically challenging? Right? Like you got to do a universal wave equation calculation, which is like V equals D over T. You got to do a Pythagorean theorem calculation to get the hypotenuse. And you've got to divide a couple of numbers and then do a subtraction operation. Okay? The trick with these is obviously doing it in the right order. Okay? And knowing what do I have to do here. If ever a question asks you, do they hear a loud or quiet? It's an interference question. Okay? Okay? It's asking you, how are the waves arriving at the observer? Are they arriving in phase or out of phase? And you just have to determine that mathematically. Okay? Like I said, there's always one of these on the unit exam because it tests several things. Okay? It tests universal wave equation. Sometimes even in a question like this, I won't give you the speed of sound, I'll give you the air temperature instead. Okay? And make you use the V equals 332 plus 0.6 T formula. All right. All right, write that one down, give it a try. Just like the one we just did, okay? But gives you another example to kind of try and have in your notes. So the speakers are 7.71 meters apart. Okay, observer is 6.9 meters directly in front of one of them. This is not drawn to scale. Okay, so that's where the observer is. Okay, obviously we got sound going this way, so we'll need to know that side. So that'll be square root of 7.71 squared plus 6.9 squared. All right, so that side's 10.35 meters in length. We know the frequency, 147.8 hertz. Okay, and we know that the speed of sound is 340 meters per second. So we got to get lambda 340 over 147.8. All right, so the wavelength is 2.3 meters. All right, so what I've got to figure out then is how many wavelengths from each speaker. Okay, so 6.9 divided by 2.3 should be 3 wavelengths. Agreed? Okay, and 10.35, is that 4.5? Yeah. Yeah, 4.5. Okay, so 4.5 wavelengths. Okay, we got 1.5 difference, so that's quiet.
Fire drill.